Computer audio. Start video. Looks like I need to adjust that a little bit. Oh, Darren is here. All right.
Good morning.
Good morning. It's a beautiful day out there. We should be going on a picnic or something.
I wouldn't know. I've been sick with, I think, just like allergies and stuff, so I haven't been outside in a while.
Oh, yeah. Well, when is the worst time? It's kind of in the fall, isn't it, for allergies?
I get them both in the spring and the fall. It's it's absolutely fantastic, let me tell you.
Well, I had, when we moved to Tulsa, I guess 39 years ago, I had allergies, but then they just went away, and I don't know what I did. I wish I could tell you, but I haven't been bothered with them since. Maybe yours will go away. That'd be nice.
Just grow out of it, hopefully.
Yeah, that'd be good. Well, let's see who else we got on board here. Let's see. We've got Ben. Ben is with us. It's just Ben and Darren right now. We're going to do strength of materials here in a minute. Do you guys have any questions or anything that's bugging you about the course?
Just wanted to make sure our midterm or whatever is the 18th. Wait, no, that's not right. Huh. I thought the. Oh, is it the 18th?
Darren, are you talking about our next test?
Yes, sir.
Well, let me look it up. This says the next test is on chapters 3, 4, and 5. It'll be available October 15th.
Okay.
And is due the 18th.
Okay, that makes a lot more sense.
I should write that down. What is today? It's the 6th. So next Tuesday will be the 13th. So that test will be available a week from Thursday. And then it'll be due the 18th, which is a Sunday. Okay, your exam is it's on chapters 13, 14, and 15. I think we start on 15 today. I believe that's right. And let me look and see here. Yeah, I think we start on 15 today. Yeah. Oh, no, wait a minute, that's crazy. No. I'll get this sorted out here in just a minute. No, chapters 3, 4, and 5. No, not 13, 14, and 15. Chapters 3, 4, and 5. Yeah, that's better. And it'll be available September. Well, not September. It'll be available October 15th. It's available. And it's due Sunday, October 18th. Over chapters 3, 4, 5, and we start 5 today. Yeah, now Darren, did that answer your question?
Yes, sir. Thank you.
Great. Oh, we got some more customers here. Ben and Ashley and Ben Harris and Ben Seaman. Darren. Class hasn't started yet. Do you guys have any comment or question for me? Because if you do, I'll try to answer it. Now we got a minute or two before class starts. Now's your chance. Well, okay, I guess we'll just get started then. But we're going to study chapter 5. Today, the topic is torsion. Is that what they say chapter 5 is? Let's look up chapter 5 and see what it says here. Yeah, how about that? That's the name of the chapter, torsion. Yeah. Okay. Be nice to know what torsion is. All it is just an external twisting. It's an external moment and that causes a body to twist through an angle. See, torsion is external. And torque is internal. Torsion is external. Torque is internal. Probably the most important equation in our chapter is called the torsion formula. And I'll show you where it comes from here in a minute. And it goes like this. And I'll try to explain what those different symbols mean. Of course, you know what that little tau stands for. Here, let me ask one of my Excellent students. How about my friend Samuel? Unmute and say hello, please. Earth calling Samuel. Come in, Samuel.
Hello.
Hello. Hey, Samuel, what's that little Greek letter tau represent?
Shear stress.
He's got it. He has got it. That is shear stress. And Samuel knows that this whole course is all about stress. Stress is where it's at. It's the most important concept because, see, stress causes things to fail. Stress causes problems. And this is called shear stress. And it's equal to torque times this little Greek letter rho, which represents the distance from your centroid, or you could think of it as your center of mass of your body. And this thing here is called your polar moment of inertia, but we'll get to that in a little while. So that's for sure one of the big concepts that we're going to study. But let's see how we can get at this torque here. Let me find you an example of torque. Let me shop around here. Okay, well here's one here. This will work. This is problem. We'll just do this problem here. This is problem 5-7. Let me make a little room here. If you missed that, you could watch the YouTube video. All that stuff is on will be on the YouTube video. My daughter will put it on there later. But this is 5-7, and they've got a circular rod here, and it has looks like some gears actually. These are gears, and they represent a external torsion. There's an external torsion on those two gears going like that. This one's 300 Newton meters. This one is an external torsion of 600 Newton meters. Now this one, it looks like another gear right there. It's going the other way. They didn't tell you what it was. Just a minute, let me read this. Shear stress in the shaft determine the radial line. Oh yeah, they told us that T1 is 2,000 Newton meters. And then finally, there's another gear here, and it's got 900 Newton meters. But see, this is connected to a fixed connection, and it can provide an external torsion. Also, think about it now. Let's see if there's 900 and 9. That makes 1800 going that way. There's 2,000 there. Wouldn't you have to have a 200 Newton meter torsion doing that? Does that all add up? Does 200, 300, 600, and 900 add up to 2,000? That's my question. Gee, I don't know. My brain is mush. I'm going to add them
Yes.
up. 200 and 300 and 600 and 900. Yeah. Yeah, we have equilibrium. See, these aren't forces, though. They're twists. They're moments. See, the sum of the moments have to be 0. Now they call these things torsions. See, torsions are external. Torsion is external. But see, in the torsion formula, the shear stress is given, maybe you don't understand that formula yet, but you will. It's given by the torque. We got to get the torques. Now, I've got a better way of expressing these torsions, and that's using double arrowheads. I don't think the book does that. But see, if you twist something that way, you're going to have a double arrowhead going to the right of 200 Newton meters. Now, if you twist something that, well, that's the same deal. This is going to have a double arrowhead going to the right. And this one too. Holy cow. All three of those. They got a double arrowhead going to the right. But now this one. See, if you want to know which way it goes, just think of a right-hand screw. You know, righty-tighty, lefty-loosey, right? See, if you take and you turn a right-hand screw like that, it will travel that way. See, so this one's got a double arrowhead going to the left of 2,000. Now this one, we're back to a double arrowhead of 900 going to the right. Okay, well, do you understand that this is a superior way of doing these torsions? We're using double arrowheads. And now we can do our torque loading diagram. This is going to be the torque loading diagram. And remember now, torque is, it's not external, it's internal. And so we're going to do the torque loading diagram. Okay, and this will be torque, and this will just be a x coordinate going to the right. And like with all loading diagrams, what you do is same thing we did with the normal force. To make to make a loading diagram, they're all alike. They're all alike. Let me go to one of my excellent students here. How about we pick on Mohammed? Mohammed, unmute and say hello, please.
Hello, Mr. Griffin.
Hello, Mohammed. Mohammed, do you remember how to make loading diagrams? What do you have to do to make a loading diagram, Mohammed?
Normal loading diagrams, we cut the beams into sections and find
Yes,
the
yes,
internal.
Mohammed's got it. You have to make a section. Now, the agreement is you always do a left-hand section. So see, you sectioned it in here. Here we go. Forget about everything to the right because we're just looking at that left-hand section. Can you see that you're going to have a double arrowhead going to the left there of 200? So I'm going to make it 200 negative because it's going to the left. Now we're going to section it in here. Now, if you sectioned it in there, can you see you got 200 and 300 going to the right? So you're going to have 500 going to the left. Well, this jumps down to 500. There, negative 500 Newton meters. Now we're going to section it in here. And you got a 200 going to the right, 300 going to the right, 600 going to the right. That makes, is that 1100? Yeah, that makes 1100. You've got to have 1100 going to the left. So it goes down to here, way down there, way down low. Does that even show up? Yeah, that shows up. Okay, that's negative 1100 Newton meters. See, we're plotting torque. This is called a torque loading diagram. And then what do? Well, if you sectioned it in here, we've got 1100 going to the right, 2000 going to the left. So I'm a little bit confused now. Just a minute. You got 1100 going to the right now, 2000 going to the left. So that's a total of 200 going to the right. So you got to have, I'm having trouble. Just a minute. I'm going to section it in here. I've got 500, 1100 going to the right. And 2000 going to the left. So I need, so that's a total of 900 that I need going to the right, a total of 900. So that means that in here, you got to have 900 going to the left. So this pops up to 900. It's right about here. And that's a negative 900 Newton meters. And is that right? Let me think about it.
Wouldn't that be a positive 900?
Yeah, you're absolutely right. Now, who said that? Where'd that voice come from?
The Ben Harris.
Ben Harris. We'll give Ben a nice big fat thank you point. We got to travel up 2000, Ben, and that puts us all the way up to I don't know, about like that. I was wrong. This is a positive 900 Newton meters. And now, to make it pretty, we can color it in, make ourselves a nice torque loading diagram. We'll make it pretty. Ta-da! You're looking at it. You're looking at a nice torque loading diagram. See that right there? That's torque. That's internal. These red things here, these are torsions. They're external. And my students can get confused on this. Like for instance, you look here and you see a 300 Newton meter and you think, well, I bet you that's what I need in this equation, 300 Newton meters. There is no 300 Newton meter anywhere on this diagram, is there? Nope. Hey, you see that 600 Newton meters? There's no 600 Newton meters on this diagram either, is there? No. So that's how you do it. You know what? It's exactly the same process that you use with your normal force loading diagrams. Did you know there are 4 kinds of loading diagrams? Is there any question on any of that? You're okay with it? All right. Well, here, I'm going to list the 4 kinds of loading diagrams. Did you know there are 4 kinds of loading diagrams? Now, on your homework, if you don't do the loading diagram, what's going to happen to you? You don't get a 4. That's what happens to you. I want the loading diagram. Now let me go to one of my excellent students. I'm going to go to Julian. Hey, Julian, unmute and say hello.
Hello.
Hey, Julian. Julian, do you know any of the different names for the loading diagrams? Give me some. Go ahead. I'll write them in here. Julian, go.
Ooh, torque.
Yeah, there's one. There's good going, Julian.
Crazy.
Good going. There's a torque loading diagram. Julian, can you do another one?
Shear.
There's a shear loading diagram. Excellent. I think Julian maybe has been listening to me. Give me another one. Uh-oh, we're drawing a blank here.
Is there?
There's 2 more. Isn't it funny when you're asked something, your mind just goes blank?
Yeah, I don't think I can think of the other 2.
Well, you've done some. There's one called a normal
Normal
force
force.
loading diagram. Now, can you think of the last one?
No.
That's all right. You're not alone. There's some others out there. That's why I ask you this stuff. It's called the bending moment loading diagram. There's 4 kinds of loading diagrams. Now, you've done these normal force loading diagrams, but these torque loading diagrams might be new to you. But good going. Okay, well, let's attack this torsion formula, shall we? Any comments or questions from anyone? All right, well, we're going to do, look at that thank you point there. That came in handy. I forgot what it was for, though. Forgotten already. Okay, now the topic is this, probably the most important equation in the chapter. We're in chapter 5. Chapter 5, and the topic is torsion. And let's say you had a rod, okay? We're looking at the cross section here, and This rod goes way back here someplace. And let's say somebody is going to twist it. First of all, before we twist it, let's put a stripe right down the middle. There we go. And now we're going to twist it. Somebody's going to come along and put some torsion on it like that. They're going to twist it like that. Of course, this other end needs to be attached to a wall or something where it can't turn. It's going to stay put. But if you do that, now another way of writing that is with a double arrowhead. Instead of writing the torsion like that, you could write it with a double arrowhead. But where do I put my arrowhead? Let me go to one of my excellent students here. Shane, unmute and say hello, Shane, please. Earth calling Shane. Come in, Shane. Uh-oh. Maybe coffee break. Samuel, unmute and say hello, Samuel.
Hello.
Hello. Samuel, I need to put a double arrowhead on that. Can you tell that's a red? Yeah, you can sort of tell it's red, isn't it, Samuel?
Yeah.
Now, Samuel, where do I put my double arrowhead? Which end do I put my double arrowhead on, Samuel?
Like coming out of the board.
Yes, good going. Samuel's got it. By Jove, he's got it. See, if you twist something like that, well, what do they call that? Counterclockwise. If you had a screw or a bolt or a nut, if you twist it like that, it comes out. It comes out. It's lefty loosey, righty tighty. Isn't that how it goes? And see, if you twist it this way, the right hand rule or a right hand screw will come out of the board. So there you have it. Good going. And here's what's going to happen. This line here that I drew along my rod, it's going to kind of move over a little bit. It probably doesn't curve like this. Let me try that again. It's going to come over here like, yeah, maybe like that. Yeah, there you go. That kind of makes sense. If you twist it, that line that I drew on there to start with, it's been kind of shifted over a little bit. And this distance right here is equal to, if you said this distance here is a radius, or in this case, we'll call it rho. And it's an angle theta there, all right? Maybe d theta, or I guess theta. Make it theta, there you go. This little distance here is rho times theta. Remember the, what do they call that? The arc length? The arc length, a formula that we all know and love. You can make that an R if you wanted to, but it's that little distance there, S, we could call it, from here to here, that it's been moved, is it's equal to r theta. S equals r theta. That's the arc length formula. If you call this distance x going this way, then the normal strain. Remember, normal strain is deformation over length. So is normal stress. Normal stress is deformation over length. But the difference is with normal strain, these are parallel. The deformation and the length are parallel. But with shear strain, the name of that is a Greek letter gamma. It's shear strain. The deformation and the length are perpendicular. Well, see, these are perpendicular. Here's your length, x, and here's your deformation. There's a perpendicular here. I'll draw it for you. There you go. See the little perpendicular in there. Those are perpendicular, whereas these are parallel. So the shear strain, here, I'll write it out for you. It's called shear strain. We've studied that before. You've seen shear strain. There's a formula with it in it. It goes like this. It goes, let's see if I can remember how this goes. There you go. It's a form of Hooke's law, where this is your shear stress, this is your modulus of rigidity, and that's your shear strain. Just like this formula here is another form of Hooke's law, where this is normal stress, modulus of elasticity, and normal strain. Right? Right. We know that. Okay. Well, we could just write this as, well, I think the way they write it is, see, rho can be any distance in here from the center to whatever point you want to talk about. If you go all the way to the end there, that would be the radius. But see, this would be rho d theta dx. That's your shear strain. Rho d theta dx. Now let me see if that's in your book or if I'm making this stuff up. Let me dig around and see here. We're in chapter 5 for anybody that just tuned in and wonder what are we doing now? We're in chapter, well, there it is. I see that equation. It's on page 185. Only they use the symbol phi instead of theta. That's okay. It's just a dummy variable. They said d phi. There you go. Yeah, that equation is on page 185. Now in this book, of course, you know, this would be the radius of your rod that you're twisting. And they decided to call that C. So let's don't get confused. C is the, I guess, the maximum distance from the centroid or the center of your rod to the outside. Now rho is any distance. Like if say you only went halfway to the outside, like maybe from here to here. There's your rho there. Rho is just the distance from the center of your rod there to wherever you want to talk about. But see, C would be the maximum from the center to the outside. When we develop this equation here in a little while, you'll discover that if rho is 0, there is no stress. If rho is 0, and if rho is 0, there is no strain. Did you know if you twist a rod like that, there's no stress or strain at the very center. I've got a pencil here. Now I'm not going to break my nice pencil, but I could take this pencil and I could twist it. It won't break at the middle. It's going to break on the outside because, see, on the outside the row is bigger. It turns out that you get your maximum here on the outside is where you get your maximum stress. Of course, you get your maximum strain too. As you turn it, the strain is bigger on the outside. You get your own pencil and break it. Take your own pencil, twist it, and you'll discover it'll start to splinter on the outside. Go wreck your own pencils. Okay. Well, so far so good. We've come up with this equation here now. Now let's see if we can continue on. We're about a third of the way through showing you the torsion formula. That's what we're studying right now. The torsion formula. And we showed you that. I need a little room here to work now. Now, what they said on page 185 is you could write the shear strain like this. This d phi dx is really going to be a constant. It's how much you twisted the rod. Once you've twisted it, keep it twisted like that. That's really a constant. But the shear strain depends on your rho. It depends on your distance from the center. See this? That's called a Greek letter rho, R-H-O. And so what they did was, if you know what the maximum strain is, which is on the outside, and you multiply by rho over c, you'll get your shear strain at any point inside your piece. See, if rho is equal to c, you have the maximum. If rho is equal to 0, you don't have any strain at all. So there's a nice little equation for strain. Now, if you go back and stare at this equation for a minute, which is Hooke's law, then we can write this equation here. Because stress is directly proportional to strain, we can write the formula for shear stress as being directly proportional to the distance from the center, just like shear strain is. If you understand that, we're getting towards the end of our torsion formula, and we'll have it. This equation you'll find on page 186. Okay, now we're ready to find the total torque acting on a piece like this. Now that we have this equation, let me make some room here and we'll do it here someplace. If you don't follow this, at least you've seen it and you have an idea of where it came from. The main thing is to be able to use it, to understand it. But what we're going to do is we're going to find the total torque, which is, remember, internal inside your piece. Remember a little while ago we found the torque on that problem, I forget the number. And we had to do it, Muhammad knew how to do it. You had to take sections to get at it. But here's our plan. We're going to take and add up all the little itty bitty torques on a cross section. Now, here's the plan. Take a little area here, call it DA. That's a nice name for it. It's just a little chunk of area. Now it's at a distance rho, and that little area is going to have a shear force on it. I'm going to call that dV. And you all know about moments. Moments, a torque is just a moment. And the torque on that little piece there is going to be rho dV. I hope that makes a little bit of sense. It's distance times force. That's what a moment is. And if you add them all up, you get the total torque. Okay. Well, this shear force, I think that shear force is equal to your shear stress times your area. That small amount of shear force is your stress times your area. All right. So why don't we write that? Shear stress times your area and have I fouled up yet? No, I don't think so. I think I've forgot my row though. Now I think I'm okay. All right, now what? Well, you see this right here? I'm gonna stick that in here. I'm gonna take that and I'm gonna stick it in there. Okay, here goes. So your your total torque on your whole cross section will be rho times rho over C tau max dA. And did you make it to there? Were you able to get to there with me?
Yep.
Yeah, there's somebody. Great. Okay. Well, I'm going to pull out the constants. Tau max is a constant and C is a constant. I don't know what tau max is, but whatever it is, it's fixed. There's only so much maximum shear stress that you're going to get because of this external torsion. And C is a constant. I can pull that out. And what you got left is rho squared dA. The torque is equal to that. Hey, we got about one more step to go. In fact, you'll see this equation on page 187. You could look at that equation. There it is. I see it. Well, I'm going to finish this up now, but I just need a little room. So let me make some room. Here we go. There's lots of room right there. Now we're going to call this, we're going to give it a special name. We're going to call it J. We can call it anything we want to, but we're just going to call that thing J. So what we have is the total torque acting on a body, on a, say a rod that you're twisting, is equal to this times J. Yeah, okay. It's got a name. It's called the second moment of area, if you really want to know. That's the name of it. It's the second moment of area. It's also, it's got a fancy name. It's called the polar moment of inertia. But we'll talk about that here in a minute. Now, see if you can do a little algebra with me and get to here. were you able to get from here to here? Were you able to make it? Okay, great. Now, do you see this equation down here that we all understood a little while ago? What I'm going to do is I'm going to substitute that tall max in this equation. Did you follow that? All I did was I took this. I got lost now. What did I do? I took, oh, okay, here we go. You see that tall max? I stuck that down in here is what I did. And if you do that, well, this is what you get. Hey, look at here. Those little C's go bye-bye, don't they? And here's what you have left. You have left the shear stress on a torsion member is equal to T rho over J. That's it. That's the most important equation in the chapter, and it's called, it's got a name, it's called the torsion formula. Ta-da, there it is. Now let's see if we can work a problem with it. Okay, let me find one here that looks interesting. This is problem F55. Let's do it. I need some room. We have our torsion formula, and we're going to do a problem now. I forgot to ask if anybody had any questions. Does anybody have any questions? Okay. Well, this is problem F55. It's a fundamental problem. Help me find it here. I lost my page here. F55. I can't find it. I'm still looking. Hey, I found it. It's on page 198. Okay, well, they have a shaft that's it's got some external torsions on it, all right. Here, let me draw it. There's this shaft. And I'm just going to go ahead and use the double arrow method of drawing these external torsions. Now the way they draw it is they go like that. And I need to know which end of that that external torsion that I put my double arrowhead on. And let me go to one of my students here. Jackson, unmute and say hello, please.
Oh.
Yeah, hey, Jackson. Jackson, they've got, the way they write these external torsions is like that. They're twisting it like that. Which end do I put my double arrowhead on, Jackson?
You put it on the right end or
Man, you
going
guys are
towards the
good.
cylinder.
You guys are good. See, if you take a right-hand screw and you turn it like that, it goes to the right. Let me show you that again. If you twist a bolt or a screw, right-hand screw, and you turn it like that, it goes to the right. So Jackson's right. Okay, well, let's do the rest of it here. I got lost here. Oh, there's another one here. And it's going to the right also. All right. Ah, but then there's one here that's going to the left. And finally, this one's going to the right. Now, if I got any of those wrong, somebody speak up and tell me. And here's the numbers. This is 600 Newton meters. This one is 1500 Newton meters. See, these are moments. They're twists. They're called torsions. They're external. This one's 1500 Newton meters, and this one's 600. Now, first of all, let's make sure that the sum of all the moments is 0. 2100. Wait a minute here. I don't think they add up to 0. There's something wrong here. 600 and 1500. That makes 2100, right? And what's no? Wait a minute, guys. That doesn't add up to 0, does it? Something horribly wrong here.
Is
The
one
book
on the
might have
very
made
end
a
facing the
horrible
right way?
mistake here.
Is the 600 on the very right supposed to be pointing to the left?
You know what? I bet you they goofed up. They did. The book made a mistake, guys. They got it going the wrong way. This thing should be going that other way, and this double arrowhead is going to the left. Now, I think it works. The 600 and 1500 make 2100. Oh, yeah. 600, 1500, yeah. It works now. Make a note in your book. It's a pretty good book, but this is wrong. It's going the other way. Y'all, little Southern talk. Y'all understand that? Book was wrong. It happens. Books can be wrong. Okay, now let's do our torque loading diagram. Here we go. Okay, now let's see. When you section this in here, you have to have it going to the left 600. There you go. Negative 600 Newton meters. We're doing the torque loading diagram. And then what happens is it, oh gee, it goes down, doesn't it? Maybe I shouldn't have made that quite so small here, or so big. Here's 600. Yeah. There's 600. It's a negative 600 Newton meters. And then it goes down all the way down to a negative 2100 Newton meters if you sectioned it in here. And then it pops back up 1500 which are back to negative 600. Negative 600. And da-da, you're done. You can color that pretty if you want. And now we're going to answer their question. They wanted the maximum shear stress in the shaft. Well, we have the equation. You're looking at it. And they said, yeah, here we go. This in here is a pipe. It's a pipe, and it has 30 and 40 millimeter radii. This here is, I like meters, it's 0.03, and this here is 0.04, right? Isn't that what they said? Yeah, yeah. Okay, now we need to develop these formulas for this thing here. The fancy name for that is the polar moment of inertia. And I would derive it for you. Remember what it is. It's the integral of rho squared dA. And I would derive it, but we got a table. It's in the flap of your book. The very flap of your book, there's a table of polar moments of inertia. You have to know how to use it, though. What they've got there in that table for a circular thing is they've got Ix is 1/4 pi r squared, and Iy is 1/4 pi r squared. This is in the flap of your book. If you'll add these, the polar moment of inertia, another way of expressing it is Iz. And what it is Ix plus Iy. And in this case, it will be 1/2 pi r squared. Okay, so do we know what the radius is there in the middle? Yeah, oh, I see it, yeah. Here we go. Now here's the problem. You're going to have to subtract. You're going to have to go 1/2 pi 0.04 squared minus 0.03. Oops. Oh, there's a thank you point. Well, we can't erase that thank you point. No, those are too rare to erase. Here, I'll do it down here. Polar moment of inertia is pi over 2. Isn't that what they said? Yeah. Well, it's 1/2 pi, or pi over 2. That's fine. It's pi over 2, but you're going to have to go 0.04 squared minus 0.03 squared. And here we go. We're going to get our polar moment of inertia. Let me do it. 0.04 squared minus 0.03 squared times pi divided by 2. Well, I'm getting an answer of 1.09956. But what are the units? What are the units? Good question. Looks like meters squared, but that can't be right. It's not meters squared. I know what it is. It's meters to the 4th, but what am I doing wrong? Oh, I see what I'm doing wrong. Here's what I'm doing wrong. This is what I did wrong. It's to the 4th power. So you have to take, this is wrong. Let me do it right. Let's see, 0.04 to the 4th minus 0.03 to the fourth times pi divided by 2. Okay, I'm getting 2.7489, 10 to the minus 6, running out of room here, meters to the fourth. The polar moment of inertia is meters to the fourth. I know that because it's equal to y squared dA. And that's meters squared, and area is square meters. So you got meters squared times square meters. That's meters to the fourth. All right, now we're going to get the maximum shear stress in here. The formula says you take the torque, which is the 2100. You can put a minus on it if you want, but I'm just after the amount. I have 2100 Newton meters times rho. Now the rho is where you got the maximum stress will be on the very outside. So that'll be a 0.04. And then you divide by J, which we did. It's 2.7489 times 10 to the minus 6 meters to the fourth. Yeah. Okay. Now I want everybody to do this. Get your calculators and solve that for the maximum shear stress in here, because that's where it's going to be. That's where you have the maximum torque. Go for it.
Professor, I have a quick question.
Yes, go ahead.
Why are we using newtons and meters and inches? I thought inches were
Well,
SI.
where do we have inches?
You have it written for the units on the bottom. I think.
Where?
Oh, my computer screen wasn't rendering it. I'm sorry. It looks like IM, but I'm sorry.
No, I don't have. I can't
Yeah,
write very good. That's a meter.
I can. Yeah, I can see the M now. It
That's
looked
a
like IN.
meter.
I'm sorry.
Yeah. But no, you don't. Thank you for mentioning that. Somebody else might have thought that was inches. Thank you very much. I'll give you a little skinny thank you point. There you go.
Thank you.
Yeah. Now the answer book says F55. They said 30.6 megapascals. This is what the answer book says. Now, let me see what I got when I did it. Here's what I got. I got 30.558 megapascal. How about you guys? Did you get that? The 30.558 megapascals? I'm waiting for it. Was that an uh-huh?
I got that.
Uh-huh.
Yeah, there's two of them. Give me another uh-huh.
Yes.
Yeah. Hey, look, we got the answer. We figured the maximum shear stress using the torsion formula. Yeah, we're feeling good about this. Okay, any questions on that before we do another one? Okay, well, let's do another problem here. Let's see. Got to find which one I want here. Let me give you a little more theory, and then we'll work another one. Now this theory here deals with power. Let me make some room. so far we've talked about the torsion formula, but there's a couple of other very important formulas in this chapter. And one of them is for power. And you know that power can be delivered with a drive shaft. Your car has a drive shaft. It may be a short one with front wheel drive, or if you have rear wheel drive, it's a longer drive shaft. But see, power can be delivered from your motor to your wheels that turn. And the formula for rotational power is torque times your angular velocity. Now to refresh your memory, for linear power, power is force times distance. Force times velocity. Power is force times velocity. I don't know if you remember that. But see, that's for linear power. We are talking about rotational power. And instead of a linear force, we have a moment, we have a torque, which is a rotational moment. And instead of linear velocity, we have angular velocity. Okay. Now that we have the formula for power, and this is all on page 194, you guys could read about it. I want to work a problem now. Now this is problem 527. We're gonna do 527 together. It's on page 203. We have our formulas for power now. We have our torsion formula. And there's a drive shaft. You're looking at a drive shaft of an automobile. It has an allowable shear stress of 8 KSI. Well, here, let me write some of this stuff down. I need that. You have that in your notes. The allowable shear stress, we don't want to exceed this, is 8 KSI. Okay, the outer diameter of the shaft is 2.5 inches, and the engine delivers 200 horsepower. Let me write that down. The power is 200 horsepower. Now we're going to have to convert that to foot-pounds per second, so let's just go ahead and do that. You know that horsepower is 550 foot-pounds per second for every horsepower. So you can get rid of your horsepower that way. And we can get the power. Let me write this down. 200 times 550. I'm getting 110,000 foot-pounds per second. That's our power. Okay, now let me keep reading. All right, 200 horsepower. It's turning 1140 revolutions per minute. Well, that's your angular velocity. It's 1140 RPM. Now what that is revolutions per minute. You all know that. You you probably have a tachometer in your dashboard that has RPM on it. See, what that is revolutions per minute. Well, we don't want that. We've got to have radians per second. So we're going to go 2 pi radians, which is dimensionless, for every revolution. You can write radians here if it makes you happy. And we got to get rid of the minutes. See, a minute is 60 seconds. So see, we can get rid of the minutes. We can get rid of the revolutions. Radians are dimensionless. And here we go. We're going to get the angular velocity. They call this angular velocity. All right, here goes, 1140. All right, 1140 times 2 times pi divided by 60. I'm getting 119.38 nothings per second. Radians per second. Radians are dimensionless. Okay, well, we're doing great. We have our, here's our equation. It goes like this. There it is. And the thing is, we know what this is. And we know what this is. Hey, we can solve for the torque. Let's do it. Now, the power is 1110,000 foot-pounds per second. Okay. No, it's 110, but I think I said the wrong thing. 110,000, and we don't know what the torque is yet, but we got our omega. It's 119.38 radians per second. We're doing problem 527. If you just sort of woke up from a daydream and or maybe took a coffee break, we're doing 527, and we're going to find our torque now. Get your calculators and tell me what the torque is. I'll shut up. Find the torque. All right, I'm going to call on somebody here. Let's see. Let's see who I want here. Brian. Brian, unmute and say hi, Brian, please.
Hi.
I didn't quite hear you. Can you do that again, please?
Can you hear me? Hi, can you hear me?
Yeah, I can barely hear you, Brian. Hey, Brian,
All
have you figured out this torque yet?
Yeah, is it 921?
Yeah, that's what I got. I got
Okay.
921.4. Now, Brian, what are the units?
Let's see. Would that be, is that foot-pounds?
Yeah, good going. Proud of you. Good going. They're 921.4 foot-pounds. We did good. Good. Now, let's see what we're supposed to do here. Just a minute. Let me read this. They want the minimum. No. Determine the minimum required thickness. That's what they want. Okay. Now this this drive shaft needs some room here someplace. We're going to make some room. This drive shaft is not it's not solid. It's not solid. And now what do we know about it? Let me read this. The shaft's outer diameter is 2.5 inches. The outer diameter is 2.5 inches. I think the formula that we use has radiuses or radii in it. And so that would mean that this outer radius is 1.25 inches. And see, what we're going to find is this inner radius. Let's call it R sub I for inside or inner. All right. And here comes your polar moment of inertia. It's pi over 2, 1.25 inches to the fourth minus R sub I to the, let me scoot those thank you points over here someplace. R sub I to the fourth, there we go. There's your polar moment of inertia for this crankshaft, but we don't know what the inner radius is, but we're going to find it. Here goes. We're going to find it. We're going to use the torsion formula. Now you know and love, or are starting to love, I hope, the torsion formula, and you know it goes like this. I'll get it right in a minute. There you go. Okay, now they said that the maximum allowable shear stress, I erased it, is 8 KSI. So we know that that's 8 KSI. And hey, we know the torque. Look at here. It's 921.4 foot-pounds. Now the rho, see, you want, if you want the maximum possible shear stress, you want the maximum possible distance from the center, rho. So that's 1.25 inches. Now here in the denominator, you got this J thing they call the polar moment of inertia. And it's equal to this here. Okay, now here's the tricky part. Here is the tricky part. Oh, it's so sad. We only have 4 minutes left. Have you ever noticed how fast time goes by when you're having fun? Here's the tricky part. You got to get rid of those feet. You have to go like this. You have to go 12 inches is a foot. And you see what that does for you is it gets rid of that foot there. And you have inches squared on the numerator and inches to the fourth in the denominator, which means you'll have pounds per square inch. That's what this is. This is 8 KSI. That's 8,000 pounds per square inch. Now we have an equation here, and we're going to solve it, and we're going to get our inside radius. You understand? Put that in your calculators, please. And see if you can find this inside radius. Go for it. Well, I wish I had more time with you, but I don't. I'll tell you what I got, though, on my calculator. I'm not sure it's right, but I got the inside radius is 1.0762 blah, blah, blah inches. That's not what they asked for. They want to know the thickness. They want to know how the thickness of the wall. Now to get that, you'd have to subtract this from the 1.25 inches. If you'll subtract it, we should get the answer. Let's see if we do. Here's what you get. The thickness of the wall should be 1.1738 inches. Now look that up in the answer book for problem 527. And they said it's 0.174. The answer book says 0.174 inches. That's how you do that problem. Any last comments or questions? All right, I've got to say sayonara for now. Here's your chance to make one last statement. Go for it. Okay, I'm going to say bye-bye, and I'll see you Thursday at 9:30, right? Sounds good. Go do your homework. See you then. Bye-bye.
Have a good day, Mr. Griffin.
Thank
Thank
you.
you. Have a good day.
You too.